All right, so we're starting out, we skip around a little bit in this class. We're going to start out with 3A, which talks about uses and abuses of percentages. This is one of the most widely used topics in all sorts of different career fields. So we need to make sure that all of these skills are good. But before we talk about percentages and how they're used, I want to make sure that everybody is comfortable converting back and forth between fraction, decimal, and percent form. So this is just a review. We're going to just fill this table in. So in the first row, you can see we're starting with a fraction, 5/8, and they want it converted to decimal form and then to percent form. So to convert a fraction, all you do is divide your numerator by your denominator. So it would be 5 divided by 8. And all you really have to do is just plug that up into, I got you, Alex. Just plug it up into your calculator. 5 divided by 8 in that order gave me 0.625. Once you're in decimal form, then it's easy to get to percent form. To go to a percent, you multiply by 100. To get out of percent form, you divide by 100. Everything is going to be 100 because percents are out of 100. So back to this. Multiply this by 100, and that basically moves your decimal to the right 2 times. So your final percent would be 62.5%. And that's it for that one. When you're starting with a decimal, I actually moved it to percent form first in this case because it's the easier thing to do. So just like the one before it, when you're going to percent form, I multiplied by 100, and that just moves your decimal over twice to the right, and you end up with an 85. Now, to get to fraction form, this is the part that people tend to forget. They forget how to do this. Anything to the left of your decimal are your whole numbers. So in this case, you don't have any. You have a 0. But if you did, anything to the left would just stay to the left, and that would indicate a mixed number. Then anything to the right of your decimal, in this case the 85, would go in the numerator of your fraction, and the place value of your last digit determines the denominator. So I'm going to switch to this real quick and go through that with you. Okay, that looks better. All right, so I'm starting with 0.85 to go to fraction form. Digits to the right of your decimal go in your numerator, and the place value of your last digit, which is the hundredths place, determines your denominator. So it sets up like that to begin with, and then anytime you can simplify, that just finishes it off. So 85 divided by 5, I believe, is 17. Yeah. So final answer would be 17 over 100 divided by 5 is 20. All right, so that's how you change from decimal to fraction form if you forgot. All right, then the third row, you're starting with percent form, so now you got to work your way backwards to both of these. To get out of percent form, you divide by 100. To go this way, divide. To go the other way, you multiply. So 121 divided by 100 is just 1.21. Move it to the left instead, twice. Then, to get from decimal to fraction form, we do the same thing I just talked about. Anything to the left will stay to the left. Digits to the right go up in your numerator, and the place value of your last number, your last digit, is your denominator. So this one would look something like this. 21 over 100 doesn't simplify any further, so you could stop right there, or you could convert it to an improper fraction if you wanted to. Multiply 100 times 1, and then add the 21. So here is what we're going to be talking about today. There are 3 ways that we use percentages. One is to represent fractions. This is the red is just an example. There's nothing to work out. Second way is to describe change, and again, it's just an example. And the third way is for comparison purposes. So we're going to go through all three ways that they're used, and I'll show you how you solve problems that involve these three different types of things. Starting with using them as fractions. So an opinion poll finds that 64% of 1,069 people surveyed said the president's doing a good job. I don't know if that's true. That was just made up, by the way. How many said the president's doing a good job? So here is a case where they gave you a percent and they gave you a total, and they're asking for what part of this survey thinks he's doing good. So whenever I know a percent and a total and I'm looking for a part, I can solve this in one of two ways, and I'm going to show you both real quick. One of the ways is to set up this percent proportion. This is just a general equation, and you plug the numbers in, you substitute into this, and then you cross multiply to solve a proportion. So since I don't know the part, but I know the whole thing, and I know the percentage, what I did was I just made the part my x, that's what I'm looking for. The whole thing is down here in my total, and the percent that was given in the problem just gets plugged in as 64. There's no need to convert this to decimal form or do anything like that. Just plug in the numbers as they are. The 100 is part of this formula, so that never changes. That will always be there. Next, I cross multiply, so it'll be 100 times x has to be equal to 1,069 times 64. Then I simplified over here on this side and multiplied this over here on the right. 100 times x is just 100x, and 1,069 times 64 gave me this, 68,416. Then my final step, since I want to isolate my x, I divided both sides by 100. That way my hundreds over here will cancel, and x will be by itself. And then this is my answer after I divided by 100. And then last, since we're talking about people, I rounded it off and made it about 684 people thought he was doing a good job. Now, when you go back and look at this, hopefully that is a reasonable answer and makes sense. So if there was 1,069 people surveyed, and a little bit more than half of them think he's doing good, then 684 is a reasonable answer for this type of a question. I'm also going to show you the other way to do it in case you prefer it this way. You don't have to do these questions both. Just pick a way that you like and go with it. The second way is to plug into this percent equation. Everything is pretty much the same. The part is still there, the whole's still there, and the percent is still there, but now the 100 is gone, like it was in the proportion. So to account for that, you have to convert your percentages to decimal form first before you can use this equation. So when I plug in, the total is still the total, the percent is still the percent, and the part is still what I'm looking for. But right here, I need to convert it to decimal form because there's no 100 to do that for me. So then I multiplied that out, and I still got the same answer. So it's really whatever you prefer. If you don't mind converting to decimal form, then this way is oftentimes faster. So that just kind of wraps up how you solve if you're talking about a percent that represents a fraction. Now to represent change, there's two different things to look at. One is called absolute change and one is called relative change. When you're asked for absolute change, what they're asking for is what is the difference between the two actual values. And what you do is you just subtract them. Put it in the order new minus old. It needs to be in that order for a reason. But that'll tell you an actual amount that it changed by, like in dollars, for example. For relative change represents the percent that it changed by. So it's still the new value minus the old value, just like it is for absolute. But now you're going to divide it by the original, or the old, and then that will take you to percent form when you multiply by 100. So they'll be the same change, but one is in a number form and one is in a percentage form. So let's take a look at some examples, and hopefully that will clarify all of this if you're confused. So, example says a diversified portfolio grows from $1,500 to $2,250. If I want to represent that as an absolute change, all I have to do is subtract the two values, the new minus the old, in that order. So the new value was $2,250, the original was $1,500. That means it's changed by $750. So it grew by $750 as an amount. As a percentage, I plug it into this one instead. So new minus old, but then I'm going to divide it by the old and then multiply it by 100 to get it to percent form. When you plug this into your calculator, do not use a percent key. Just hit times 100. Otherwise, it will do too much. Also, if you plug this into a very powerful calculator, make sure you do 2250 minus 1500 and hit equal before you divide. Otherwise, you will get something different. You want it to be 750 over 1500, which should be a 50% change. All right, so it grew by $750, which means that it grew 50%. Two different ways of representing the same change. All right, here's another one. We're going to do a few for our practice. So you bought a computer 3 years ago for $1,000. Today it's worth only $300. Describe the absolute and the relative change. So the absolute is how much did it change as a dollar. Relative, how much did it change as a percent. So I subtracted, and I need new minus original in that order, because in this case it's negative. The negatives do make a difference. When they are positive, it means it was an increase, and negatives represent decreases. On your homework, let me pull this up for just a second here. On your homework, be careful. My math lab has you plug into those little boxes when they're short answer fill-in types of questions. If your answer is supposed to be negative 700, you should indicate it with the negative sign. However, if in my math lab you see something like this next to the box that you're supposed to type in, you don't need a negative because it already indicated that it was a decrease. So it's like redundant, and it's not necessary. It's either negative 700 or it's a $700 decrease. If you put it twice, it's like doing something like this.
Will it count it as wrong?
Yep. Yes, it will. So just be careful. In a case like this, you don't need it for this same type of reason. Now, I will say this. If you know you were right, you went back and you reviewed it, and you know you were right, you just weren't sure what they wanted you to type, send me a quick email and tell me, hey, I'm pretty sure I did this correctly. Can you take a look? And I can go in and look at it. If it actually is right, I can bypass that and give you credit. So as far as your score goes, don't stress too much about it. But what I don't want to happen is you think that you're doing it wrong and get stuck and can't figure it out. If you're actually doing it right and it's marking you wrong, that can really drive you crazy sometimes. So just be careful. All right. As a relative change, you're going to still plug in new minus old and divide it by the old. Whenever you're doing relative change, anything involving the word relative, you always want to divide by the second value that you've got here. And that gave me a negative 70%, which is a 70% decrease. Okay. One more quickly for practice. So the delegation increased from 30 to 53. As an absolute change, that means it grew by 23. As a relative change, you take this answer, divide it by the original, excuse me, and there's your decimal, so that's about a 76.7 change. Also, watch for how my math lab wants you to round things, especially if you get something that repeats, check for the rounding. Okay. Absolute difference and relative difference now is essentially the same exact concept, but the words now changed from change to the word difference. The reason that is because you're not talking about an original and a new value anymore. You're just talking about two different numbers. For example, two different places, two different cities, populations, for example. One's not new and one's not old. They're just two different things that you're going to compare now. That's the only difference. As far as what order do you put them in, don't get caught up with what's compared and what's referenced. That's just the math words that they use. Keep them in the order that you see them in the question. And then always divide by whatever you wrote second. Okay, so let's take a look. So average pay for full-time wage earners varies. Recent data show that New York ranked first in average pay or at about $60,300 per person, and South Dakota ranked last at about $32,800 per person. We want you to compare the average pay in South Dakota to that in New York in absolute and relative terms. So notice how they ask the question, South Dakota to New York. That's how you know the order that you're going to put these numbers in. South Dakota will come first, minus New York. So as an absolute difference, just subtract them in that order, which is negative 27,500. And all that means is that South Dakota, compared to New York, makes this much less, because it's negative. As a relative difference, plug them in South Dakota minus New York and divide by the second, which is New York. And everything is the same from before. That represents about a negative 45.6 difference, which means South Dakota makes about 46% less if you round it off. All right, so here is another quick one for practice. So the number of deaths due to poisoning in the U.S. in 2009, which is 39,000, is blank percent greater than the number of deaths due to falls. So on the homework, this is kind of similar to what the homework will look like. You might have it worded either way. They'll specifically ask you for absolute or relative, or they might say something like this and give you a blank. See how they're putting the percent sign next to this and just giving you one blank? That means they only want the relative change, because that's what that is. Relative change is the percent change. So keeping it in the order that they gave it to us, I subtracted the first minus the second divided by the second, and then I got this decimal. So as a percent, I multiplied by 100 at the end and rounded it, and just round according to how my math lab wants. So it's about a 49.4% difference, or 49%, depending on how they want you to round it off. All right. We're still going to talk about absolute and relative now here for these questions too. But now what's different about this is now the numbers that you're starting with are percentages, and it makes it very confusing for students, and it's a little bit tricky to kind of explain it. So all I'm going to tell you is when the examples that you're working with start out as percentages to begin with, just make sure you label absolute answers with the word point on the end of it. So I'm going to actually work all of this out on the whiteboard so you can see what I'm talking about. So just bear with me for 1 second. Go back over here. All right, so here is the example that they asked for, 3% to 4%, and they want it as absolute and relative. But what if it was $3 to $4? Just hold this top thing off for a second. If it was $3 to $4, as an absolute change, we just subtract. So that means it changed by $1. It went up by $1. That's hopefully not too bad. As a relative change, I'd still plug this in the same order. And then I divide by the second one. And then I multiply by 100. So let me show you what that looks like real quick here. I'm going to do 4 minus 3 first, then divided by 3, and then multiply it by 100. That looks a little blurry, but here's what I got. 33.3 repeating. All right, so since we use the same numbers, we know that the absolute answer will be a 1 and the relative answer will be 33. So now let me try to go back and explain what I'm talking about with how you're supposed to label these answers when you're looking at percentages to begin with. Slide this over. All right, so if I'm going from 3% to 4%, I'm still going to subtract. And it's going to give me my answer of 1. If I try to label it with a percent, that is very misleading because we already know the percent is supposed to be 33. How can it be 1% and 33%? It can't be. So the problem is when you're dealing with percentages and you're doing change questions on them, you've got to label them specifically so that it's not misleading. This changed by 1 percentage point. So you put the word point on the end. And this is, which represents a 33% actual change. All right. So one more time, just make sure the absolute answers when they're involving percentage has the word point onto it. Okay. Let me just did that. So let's do a new one here. So due to recent tax cuts, income tax for a certain bracket went from 28% to 25%. Describe absolute and relative changes for those two percentages. So for absolute change, nothing crazy, just subtract them. 25 minus 28. Concept's still the same, it's still -3. We'll put the word point on the end. Then for the relative change, still same concept, subtract them, divide by the second one, multiply to get to percent form. That's a -10.7% change. So it decreased by 3 percentage points, which is a 10.7% decrease in the relative terms. So now, here's how you can use percentages to compare two different things. So we went through how you use them for fractions, we went through how you represent them with change, and now how do you use them to compare. To compare, you use either 100 plus or 100 minus p. P represents the percentage in the question, and you use the plus anytime something is an increase or something goes up, and you use the minus to represent comparative values when they're going down or decreasing. So here is an example. Carol earns 50% more than William. How many times larger is her income than his? So they just want you to compare her income to his. When you see more than, that means she makes her salary is obviously higher, so you're going to use the 100 plus. And literally that is all you do. 100 plus whatever the percent was, 100 plus 50 is 150. So she makes 150% more than he does. Usually we say 1.5. We usually use decimal terms when we're speaking, but both of these answers are correct. As a percent, it's 150. As a decimal, it's 1.5. Literally, that is it for that question. A store is having a 25% off sale. How does that price compare to the original price? So again, you're being asked to compare. So you're going to use the 100 plus or the 100 minus. Now, since it's a discount, the discounts come off of the price, you're going to use the 100 minus. And literally just plug in as 100 minus 25. That's it. Answer is 75%, or 0.75. So, as a compared price, sale price is 75% of the original. So here's an example of that. You purchase a shirt for $21. The local sales tax rate is 6%. What's the final cost, including the tax? Most people, if they know how to do this, most people break this down to 2 steps. They first find the tax, then they add it on. Very common method, and there's nothing wrong with it. If that's what you were thinking, you can still continue to do it. It'll always work. But what I'm going to show you is how you use the 100 plus and the 100 minus to shortcut it and get your final answer in 1 step instead of 2. So first, let's go through the traditional method with the 2 steps and what people are used to doing. It goes back to this idea. You can solve for the part with this equation that we talked about before. Since we don't know the tax initially, we just know the total and we know the percentage. We could find the tax if we represent the part as that and the whole thing as the cost of the item. So I plugged in 6% in my percentage spot. My cost is 21. I have to convert this to decimal form since I'm using the equation method right now. So I did that next. And then I multiplied to get my sales tax. So sales tax on this $21 item would be $1.26, which then means for my final cost, I just add that on. My final cost would be $22.26. Again, that's how most people would work this question, and there's nothing wrong with that. It's how the receipt would probably print it too, so that's why people usually do it that way. The shortcut method is to do the 100 plus in this case. I'm using the plus because taxes are added on. If I'm talking about discounts, price reductions, anything involving a decrease, I would use the minus instead. But for this one, since taxes are added, I'm going to use the plus, and I'm still going to use the same amounts for everything else. So the P is a 6, the reference value is now the cost of my item, and the compared values become my final cost. So there is not going to be any intermediate step. I'm going to go right to my final cost this way. I added this up, and then converted it to decimal form, then multiplied. And my final cost is $22.26, just like it was with the other method. But again, I don't have to do 2 steps. I don't have to find the tax and add. I just do 1 step and I'm done. Here's another one, just like that. And it's sales tax again, so we're going to do the 100 plus. So the new lawnmower has a price of $648 with a local sales tax rate of 7.6%. What's the total? So they're asking for that. You could do it either way. You can do it with a 2-step or the 1-step. I did it both ways actually. So I did the 648 times my 7.6% in decimal form, which gave me my tax. Actually, here let me pull this up on the whiteboard real quick to show you where all this came from.
Have the 1 in that second part for the decimal, like the 1.076.
Well, that's how you do it if you're gonna do it in the 1-step. Here, let me do it.
I would just times it by like 0.076 if that makes a difference.
Well, let's go here. That's what I'm trying to show you, is you can do it either way. If you do it with hold on. If you do it with the 0.076, like you said, and then multiply by 648, that should give you the tax that I had before, 0.076 times 648. It gave me $49 and about 25 cents. This is tax, which then means I got to do the second step and add that on. So it would be 648 plus the tax. Oops. 648 plus 49.25 gave me $697 and 25 cents. So that's your total. And again, that's usually how people are used to doing it. They take their tax in decimal form, multiply it by the price, get their tax, and then add that on. What I'm attempting to show you with the other method is add the 1 on right off the bat instead, and then multiply by your price. And you still get it. You just do it in one step and it's faster. Does that make sense to everybody else?
Yeah, I think so.
Okay. All right, so oops. Okay, so that's the end of it. We're going to move to the last part of this section right now. So here is, at the end, we're talking about now abuses of percentages. There are lots of different abuses of percentages. We're going to talk about one specifically, and that's the shifting reference value here. This is the one that is most commonly abused, I guess you could call it. For example, if you have a 10% pay cut followed by a 10% pay raise, oftentimes people think that that brings you back to where you started with, but it does not, because when your reference value shifts, for example, your base salary becomes lower, 10% of a lower amount is less money. So a 10% pay cut followed by a 10% pay raise is not going to put you back at where you started. You'll actually go slightly lower. You'll be close, but you'll be slightly lower. And I'll show you how you could figure out what you really would be. Also, people do things like this. They talk about less than nothing when percents are involved, and there's no such thing as that. You can't decrease your caloric intake by 150%. Because if you decrease it by 100%, that means you've decreased it completely. There's nothing left. You can't eat less than nothing. That makes no sense. And things like this don't work. Averaging percentages, you can't do that because you don't necessarily know your reference values here either. So you can't take 70% of boys and 60% of girls in a class and average it together and say that 65% of them voted to go, because you don't know how many boys there were and you don't know how many girls there were. So it doesn't work that way. You need to know the reference values first. So let's, as I said before, let's talk about this shifting reference value thing here. And we're going to figure out exactly what's going on. So a stockbroker offers the following defense to his angry investors. I admit that the value of your investments fell 60% during my first year. However, this year, their value increased by 75%, so now you're actually 15% ahead. That's what he's saying, and we're going to evaluate whether or not we think he's right. A lot of people would actually buy into this and be okay, but let's see what happens for real. There's some steps that are on the notes page that are not on my PowerPoint that I'm going to jot down real quick over here on my whiteboard for how you solve things like this for shifting reference values. Okay, so if you're taking notes along with me, definitely write this down. All right, the first thing you want to do is convert your percentages to decimals. So if you go from a 10% pay cut to a 10% pay raise, you're just going to take those two percentages and put them in decimal form. If you're going from 60% to 75%, you're going to put them in decimal form using this whole idea. Okay, so increases are the plus and decreases are the minus. Then we go to multiply those decimals together. That's going to give you an amount that something is actually changing by, like, from a comparison standpoint. Then we're going to subtract 1 from that to figure out what actually happened with the change. This will always be subtraction and it will always be 1. It doesn't matter if it's an increase or a decrease. This is just, we're taking the 1 back off that we manipulated up here with the 100 plus and the 100 minus. We're undoing what we did right here to get us back to where we want to be. And then we're going to convert back to percent form. And that'll tell you what we really are at then when we end. Let's go back and we'll take a look at this thing again now. All right, so we got a 60% decrease right here. It fell 60%, and then it increased 75%. So keep that in mind. So for year 1, we had a 60% loss. So I used 100 minus P when I plugged it in. So I used 100 minus 60, in other words. 100 minus 60 is 40%, and then I converted to decimal form. Then I'm going to put that aside and do the other year. Year 2 was a gain of 75%, so I used the plus, and then it's going to be 100 plus 75, which is 175%, and in decimal form, that's 1.75. Now I have these 2 changes that happened in decimal form. That's step 1. Step 2 is to multiply those 2 decimals together. So I took the 0.4 times the 1.75, that gave me 0.7. This is what it is from a comparison standpoint. Your stocks are actually worth 70% of what they used to be. When you subtract 1, that tells you what it changed by. That means that we actually lost, the negative is a loss, we actually lost 30%. We are not 15% ahead, we are 30% below, and that stockbroker needs to be fired. So here is one more, just to get a little bit of extra practice in. We got an, let's see, last year company increased its workforce by 40%, and the next year it decreased by 35%. What was the overall decrease? So we got an increase, which is going to be 100 plus, followed by a decrease, which is going to be 100 minus. So I did 100 plus and 100 minus for those 2. I went right to decimal form here. If you are not sure what it's coming from, 100 plus 40 is 140. Then I moved my decimal over. 100 minus 35 is 65, and then move my decimal over. That's where those came from. So then I multiplied that together and subtracted 1, which means that overall, since this is negative, it was an overall decrease of 9% of the workforce then. Okay, so this is what this topic is about. 2A is how you use units of measurement, all kinds of different ones, to solve problems. And I'm going to show you 2 different methods, both of them involving proportions. Oops. Different types of fractions that you make and proportions. So if you're unfamiliar with some of these conversions, make sure you take a look at this when you're working with your homework. For example, if they ask you something about a furlong, for example, and you don't know what that is, there are some obscure ones here that you could look up. You could also just do a Google search if you're not sure. Okay, so let's get started. Here's where the first example begins. They want you to convert 9 feet to inches. Now, before I work this out, I'm going to just say I already am aware that all of you could probably just do this without setting it up the way that I'm going to do it. You could probably all give me the right answer just in your head even. I am going to show you these 2 methods with a very easy problem for that reason on purpose, so that you can understand how the methods work and set up. That way, when we do more obscure ones, like a furlong question, you do the same setup no matter what, and everything is pretty much straightforward. So if I'm starting with 9 feet and I want to convert it to inches, one of the ways you can do it is by using unit analysis or dimensional analysis. What this method does is it sets up fractions that are multiplied together in a whole string, and by setting them up in this certain way, things that you don't want will cancel, and things that you do want to change to will be the only thing left. It's a nice visual way of setting up a measurement conversion. The way you do it is you take your starting unit, which in this case would be the 9 feet. Make sure you label everything you're doing, because that drives the whole process. That's the most important part. You take your starting unit and you put it in fraction form. Since it's just a 9, and 9's a whole number, you're going to stick it over 1. If you already started off with a fraction, you wouldn't need to do that. Just make sure your starting numerator is the thing that's labeled. You shouldn't have anything down here necessarily. Sometimes you will, but most of the time, 99% of the time, you don't want anything down in the denominator when you begin. Then, this method requires you to multiply. So, let me get a different one here. Okay, so we're going to set this next one up using a conversion. So this is always your starting unit. This one is always going to be a conversion. What do I mean by a conversion? I mean the fact that there are 12 inches in the foot. Okay, but the labels make a difference. So we started with feet here up in the top. That means feet have to go down here in the bottom, because those are the ones we want gone. We want those to cancel. If they're diagonal, they will. The new unit that we want is inches, so that will go up in the top. And then I'm just going to fill the numbers in where they belong. So the 12 goes with the inch, and the 1 goes with the foot. So there's my initial setup. And again, most important thing, make sure the thing you don't want anymore is diagonal so that they cancel out. Now, when you multiply fractions, you're supposed to go straight across. So it's going to be 9 times 12 over 1 times 1. Taking something straight across is what cancels the feet, and the only thing that's left that didn't cancel out is now the inch. So that gets put on the end of your answer. So 9 times 12 is 108. 1 times 1 is just 1, which means that we can simplify this and just make it 108 inches. And that one's done. Let's try it. There we go. That's much better. All right, so that's the first method. That's called unit analysis. It sets up everything that gets set up diagonally. The nice thing about this method, and this is the method I prefer, I do all of my conversions this way, is you can use this method whether you're doing a one-step conversion, and it's just a straight shot like this, and you can do this setup if you're doing a very complicated conversion that requires lots of different conversions. You can just string them all together and be done with it also in one step. The other method I'm going to show you is just setting up proportions, and it's perfectly fine. Problem with it is if you have a more complicated one, you have to do several setups, and that can get a little bit, it just can be a little bit time consuming when you have to do it that way. So one of the ways that I like to start is to take my starting unit with this method, and I put it over what I want. I started with 9 feet. I want it to become inches. Since it's a proportion, they are equal. We're not multiplying anymore. They're now equal. And that means that the feet stay in the top and the inches stay in the bottom. Hold on a second. The train is still going? Yeah. Okay. And I'm still teaching, so you need to be quiet. Okay, now when I go to fill this in, 12 inches goes down here, equals 1 foot, that goes up there. To solve a proportion, you cross multiply. We looked at that before when we were looking at the percent proportion problems. So it's going to be x times 1 equals 9 times 12. X times 1 is just 1x or x. 9 times 12 is 108. And the x represents, get out of here. The x represented inches. So you can get it that way too. 2 different ways of doing it. Either way works. You guys can pick which way you like. I do it the first way. So when I'm working the rest of them out, I'm going to probably use the first way unless you tell me otherwise. Let me go back here. Now here is an example. This one is a little bit more complicated. The rest of them will be. And I'm going to show you, we're going to work it out with the first way. So how many cubic feet of soil are needed to fill a planter that is 6 inches long by 4 inches wide and 10 inches tall? They gave you a picture there to help you visualize what's happening. It's three-dimensional. That's where the word cubic is coming from. This represents a type of a cube. All these little cubes on the inside is what they want to know. How many of those little cubes would be needed to fill this up? So let me jot down the information real quick first, and then we'll go back to the whiteboard. They want cubic feet. That's what the question is asking. They gave us 6 inches by 4 inches by 10 inches. That's great. That's it. That's all we need. So now we can work this out. Okay. So I'm going to break this down into a couple different things. First of all, when I look at the question wants cubic. We just talked about that. That means it's three-dimensional. Cubic is another word for what is the volume of this thing. So if that's what they're asking for, I have to first find the volume. Since it's a rectangular prism, finding the volume is just length times width times height. And just plug those all in. So I'm going to do 6 inches times 4 inches times 10 inches. And I'm going to find the volume because then I'll have something that is in a cubic measurement as opposed to just a regular inch measurement. Okay, so 6 times 4 is 24, times 10 is 240. Inch times inch times inch is cubic inches. That's how you read that. So there's 1, 2, 3. I put a 3 on the end, and you read that as cubic inches. So now I do have it. I have it in cubic form. The problem is they didn't want cubic inches. They wanted cubic feet. So I have to do another step and convert this. All right. I'm going to do the first method that I showed you before in order to convert. So I'm going to take the 240. Put that over 1. Then I'm going to multiply, making sure that my cubic inches are diagonal so that they will cancel out. And my cubic feet is what I want. That's going to go up here. Now, I need a conversion to fill in here. If you don't know how many cubic inches are in a cubic foot, go back here and let's see if we can find one. So we're talking about volume, so we're looking under the volume section somewhere. Liquid measurements don't help us, so we need to look at the dry measurements for volume. And I see right here cubic feet and cubic inches right here. So I'm going to jot it down on my paper real quick. 1 cubic foot is the same thing as 1,728 cubic inches. Now I have what I need, and I can finish this out. So again, I jotted down my conversion over here off to the side so that I can plug it in here. That's what it looks like. Next, I'm going to take this straight across. So 240 times 1 is just 240. 1 times 1728 is 1728. When I've done that, I've just canceled those cubic inches out, and cubic feet is all that there remains. This is your answer. It's pretty ugly, so I am going to divide this out and see what this would be in decimal form. And I got 240 divided by 728. I got about 0.14. Looks like the 8 is repeating here on my screen. So I just rounded it off. It's about 0.14 cubic feet. Final answer. Okay, so one other thing to note. Let me go back to this thing here, this conversion. If you didn't know how much this was, I'm going to show you just real quick how we could have gotten it without looking it up. If you already know the regular conversion, this is called the linear conversion. This is the cubic one. If you already know this, to get the cubic one, you just cube both sides. Basically, that means 1 times 1 times 1, which is just 1. 1 cubic foot. Let me do this. Equals And then this one is just 12 times 12 times 12. 12 times 12 times 12 is 1728. And then the inch is also cubed. So that's where that comes from. If you ever needed to find your own conversions for whatever reason, all of them start off somehow, and then you can get to the rest by just doing a little bit of calculations. Okay, let's go to the next one. Here's what I'm talking about a weird thing like furlongs. If you've never heard of that, if you don't know what that is, it's usually used in horse racing. But some people panic because they've never even heard of it and they don't know how to do it because they've never heard of it. If you know the setup, it doesn't really matter if you've heard of it or not. So the length of the derby is 10 furlongs. Let me jot that down. How long is that in miles? Okay. So here we go. They want 10 furlongs converted to miles. So let's do what we've been doing and take our starting unit and put it over 1. And then put the furlongs that I'm going to convert down in the bottom so that it's diagonal and they'll cancel. And the thing that I want, which is miles, go up in the top. Basic setup, just need to go and look this up now. If you don't already know it, just go and look it up. Miles is length. So we're looking at the length section, and here's the furlong conversion. A furlong is the same thing as 40 rods, which is the same thing as 1/8 of a mile. So that's the one we need. 1 furlong equals 1/8 of a mile. I jotted it down, and now I can use it. So when I plug it in, the 1 goes with the furlong, the 1/8 goes with the mile. And that's it for that. Now I'm just going to go take it straight across and plug this into my calculator and see what happens. So 10 times 1/8. You can plug in 1/8 just as is. If you put parentheses around it, every calculator will do it this way. 10 times parentheses 1 divided by 8 is 1.25. 10 times 1/8 is 1.25. 1 times 1 is just 1. Furlongs cancel. This simplifies to 1.25 miles then. You also have a fraction key, most of you, on your calculator, which you can plug in 1/8 just using that, and that'll probably pop your answer out as 1 1/4 instead. That's fine too. Just pay attention to what my math lab wants you to use, whether they want decimal form or fraction form, and how they want it rounded if they want decimal form. Okay, that's it for that one. Now on to the metric system. So we in the United States are a little bit behind in the times. We still use an old system. We're the only ones that use it, actually. So the name has been changed from customary to U.S. customary because we're really the only ones that use this old system. Metric is more modern, and it's pretty much what the rest of the world is using now. The reason for it is everything has been based around powers of 10, as opposed to our weird system where we've got 1 foot and 12 inches and 3 yards and 5,280 feet. It's just crazy numbers that we always have to work with. The metric system just uses tens, hundreds, thousands. You just add zeros or take them off. You can move your decimals back and forth then, and it makes it Very convenient. So one way to convert the metric system is to just know the prefix line that the metric system uses. These are all the different prefixes for the metric system. The most common ones are on something called a metric prefix line, and it looks like this. I'll explain all of this here in just a second. This is the metric prefix line. These are the most commonly used metric measurements, so they have their own little system here. K stands for kilo. H is hecto. DA is an abbreviation for deca. And this right here is where your base unit would go. The base unit varies depending on what you're measuring. It's either the meter, if you're measuring length. It could be the gram, if you're measuring weight. It could be the liter, if you're measuring liquid volume. But it could be other things too. The metric prefix line, anything you could measure, it could all go here in the base unit. For example, the watt is a measurement of power and electricity. You could use the watt as your base unit. D is an abbreviation for deci, C is centi, and M is milli. And then, like I said, there's others. There's ones that are much larger than kilo, like giga, if you ever think of computers in a gigabyte. And there's ones that are smaller than milli, like micro, and they're super, super, super tiny. They would be way over here off the line. So there's others, but this is the basic metric prefix line, and this helps you convert pretty much the majority of the metric measurements. And one more time, since these are prefixes, these would all go before the base unit. So it would be like kilogram, hectogram, decagram, gram, decigram, centigram, or milligram. What else? This is a little saying to help you remember the order. For those of you who are like me and need things like this little memory device to remember stuff, King Henry died by drinking chocolate milk. Kilo, hecto, deca, base, deci, centi, milli. Okay, now how do I use this? All I do is I put myself on my starting unit, move to where I want to be, and that tells me how to move my decimal and how many spots to move it. And that's it. It's very easy. It's a nice system. I wish we'd switch to it. So we're going to convert 2,759 centimeters to meters. So we're starting at centi, and we need to move to meter, which is a base unit. So we need to move back 2 spots to the left, and that means that's what we're going to do with our decimal. We're starting back here. We need to move that 2 spots to the left, and now we're between the 7 and the 5. So 2,759 centimeters is the same as 27.59 meters, and that's it. This metric prefix line can only be used when you're going from a metric to another metric measurement, by the way. If you're going from a US to a metric, it won't work. If you're going from 2 US systems, obviously it doesn't work because none of them are metric. You have to have 2 metric to be able to use this. So if you're reading it and it sounds the same, like centimeter and meter both have meter in them, that's an indication that you're in the metric system. One other thing that I'll point out is any move to the left on this line is like dividing by 10. And any move to the right is like multiplying by 10. So since we did 2 moves to the left, we divided by 10 2 times. Just like dividing by 100. So if you wanted to plug it in, you could do it that way too. You could just do 2759 divided by 10 divided by 10, since you're moving it twice. And that'll move your decimal for you. In case you have to do a lot of moves, sometimes people aren't necessarily the most careful, and that decimal really needs to be in the right spot. You don't want to kill anybody when you're talking about dosages and things like that. Okay, let's move on. All right, so a marathon race is about 26.2 miles. About how far is that in kilometers? All right, so here is what they're asking for. Now that I've introduced both systems that you're working with, now first thing you want to do is make sure you identify what you've got, because that'll tell you what method of converting you should be doing. You've got miles and you've got kilometers. Miles is the US measurement, kilometers is metric. So we can't use the prefix line because we got one of each. We're going to have to go back and either do the unit setup like I've been doing, or you could do proportion. So take your starting unit, put it over 1. Make sure the thing you want to get rid of is diagonal. That way it'll cancel. And kilometers is what we're trying to find, so that should go in your numerator. Now, if you don't know how many kilometers are in a mile, again, right here we need to just look up the conversion. So I'm going to go back and see if I can find one. In this table, when you're looking, the top 2.1 is the US system, and 2.3 is US to metric, back and forth between those two different systems. So I need to be looking here when I do this. I actually see 2 different ones I could use right here. 1 mile, I'm going to jot it down. I could use 1 mile equals 1.6093 kilometer. Or, on the other side, I also see miles and kilometers. So I could use this one, too. So I'm going to jot that one down. 1 equals 0.6214 miles. Okay, so I jotted them down. Let's take a look. Since I have 2, I'm going to actually do this problem twice to show you what happens if you use one versus the other, just so that there's no confusion about, well, which one do I use? You can use either one. You should get something really close, if not exactly the same. So let's go with the first one. The 1 is going with the miles, so that's going to go down here. And the top is 1.6093. And that's the first conversion just filled in. Next, I'm going straight across. So 26.2 times 1.6093. I got about 42.16. 1 times 1 is just 1, which I don't need to do anything with that. I can just drop it. So my answer is about 42.16 kilometers. That's if I used the first one. Okay, fine. Let's look at what's what would happen if I converted the same one using the other conversion. I'm still going to set it up the same way initially. 26.2 miles. We'll go over 1. Scoot over. Miles still goes down here. You still need those to be diagonal so that they'll cancel. Kilometers is what I want. That still has to go up top. But now the numbers that I fill in here are going to change because I'm going to use the other conversion. So the 1 now goes with the kilometer. And then this goes down here in the bottom. Next, I'm going to take it straight across, like always. 26.2 times 1 is just 26.2. And 1 times 0.6214 is just that. My miles are gone now that I multiplied it through. And this, since this is really ugly, I'm going to divide this and get just 1 decimal. I don't want to have a decimal fraction. So 26.2 divided by 0.6214. Gave me that. So as you can see, we did it 2 different ways using 2 different conversions. We got the same thing after we rounded it. That won't always come out exactly the same. You might be off by a digit or 2. One might be 42.16, 42.17. That's because when you go from one system to the next, you're not going to get an exact number, almost never. These conversions are already rounded off when we're using them in the calculation. So just watch for what my math lab wants you to use. Oops. And watch for how they want you to round it. So this is, now if you had to exchange currency rates for whatever reason, just as a side note, exchange rates change daily. So this chart from January 2017 is definitely no longer valid as a real conversion, but the way that this table reads is really all that matters, is how you guys are able to read an exchange rate table. So I'll go through it using this example. I'll explain how you read the table. So it says at a department store, the price of a pair of jeans is 45 euros. What is that in US dollars? So first I'll jot it down. It's 45 euros. They want that converted to US dollars. Now, if they are asking for euros, we got to find the European euro in this chart. And I'm going to explain what this is trying to tell you. The first one is dollars per foreign. So dollars per, in this case, euro. That means that it's 1.058 US dollars per euro, means per 1 euro. So that's one conversion. The foreign per dollar on the other side is just a different one that you could use. So foreign meaning whatever the currency is you're working with. It should be euro per dollar instead. And according to this, it is 0.9449 euros. Oops, let me fix that. 0.9449 euros is the same thing as $1 now. Per dollar means per 1. So here's what I need. You have 2 different conversions to use, just like the last problem that I did twice with the miles to the kilometer. You had 2 different ones to choose from. You have 2 different ones to choose from here. What some students try to do is use this as a conversion. Oops, That's not the conversion. It's this many dollars per one or this many euros per one. It's two different conversions that they're giving you there. Okay, so let's go back to it now. We're starting with 45 euros. We're going to put that over 1. We're going to put the euros diagonally. And the dollars that we want go in the top. And then we have our choice to use either one of these. So I'll just use the first one because it's first. So I'm going to put the 1.058 at the top over 1 euro. Then I'm going to take it straight across. So 45 times 1.058 gave me 47.61. Euros canceled, and then 1 times 1 is just 1. So it's about $47.61. If you traded in 45 euros, you get that much in US dollars. And again, we could do it with the other one, and we should get something really close. In fact, I'll do it just real quick. So I take 45 euros. And use the other one instead. Now this goes with euro, so that goes down bottom. The 1 is now in the top. When I go straight across for this one, I have to divide this to simplify. So 45 divided by 0.9449. Give me something really close. 47.62 instead now. Again, the homework is going to indicate what it wants you to use and how it wants you to round. So even if you're just slightly off, it might also have an answer tolerance to accept either one. If you're getting it wrong repeatedly in the homework, chances are you're not following how they want it done. So make sure you watch those navy blue instructions. So a gas station in Canada sells gas for CAD is Canadian dollars, 134 Canadian dollars per liter. That means per one. What's the price in dollars per gallon? So here's the issue. We're in Canada. They use Canadian dollars, but they also use the metric system. So we need to convert our money to US and our volume from metric to US so that we have a better understanding about how much this is really going to cost us. So we have to do two things. First, convert the money, then convert the size, and then we'll divide it at the end to make it dollars per gallon. Per means divide. Okay, so step one, let's change the money. So we're going to take the starting unit, put it over 1. Put Canadian dollars diagonal, so that cancels, and dollars are going to go on the top, and I need to look up the conversion real quick. I have the first one is 0.7586 is dollars per foreign means per one, so per 1 Canadian dollar. That's the one I'm going to use. I'm not going to do it twice again because there's no point. We don't need to beat a dead horse. All right, so dollars per foreign, dollars per 1 Canadian. This is how it sets up. Multiplying straight across. Let's see what I get. I got about $1.02 after I rounded off. 1.34 times that. Canadian dollars canceled. 1 times 1 is just 1, so I don't need that. That's about $1.02. Okay, step 2 is to convert the liquid now. I need liters to gallons. It's per liter. That means per 1. I have 1 liter to start then. I need to know how many gallons that is. So if you have a 1 to begin with, this is just a conversion you could look up with. Any conversion uses a 1 in it, so I can just look up this conversion. I don't actually have to calculate anything. Let's go all the way back up and see if there is one. I need liters and gallons. That's one system to the next, so that's this table. I have 1 liter. I need to know how many gallons it is. I see it right here. Let me jot it down. 1 liter is 0.2642 gallons. Okay, so all I did, again, was I looked it up. Since it had a 1 in it, I knew it would be a conversion somewhere. Looked it up, wrote it down. Okay, now I have what I need. I have the money. I have the gallons. I need to just put them together because it's per, so I gotta divide them to put them together. Per gallon. All right, let's see what that comes out to be. When I divided, I got about $3.86 after you round it off. So it's $3.86 per gallon. So that means gas is expensive in Canada. Okay. That's the last one. Do you guys have any questions for me right now?
Yeah, I don't understand how you got the 0.7586. Why you didn't put it over the 1.318?
1.318. Oh, from the table?
Yeah.
Right here? Okay. Hold on, let me jot it down real quick. 7586 and 1.318. Okay. Dollars per foreign, and this is foreign per dollar. Okay, let me go back now. Okay, so she's asking the question here. I used the 0.7586 with a 1 instead of the 0.7586 equal to this thing. That's because these are 2 different conversions that you could use. These 2 things are not equal. What it's trying to tell you is that this number that you're seeing here is dollars per foreign, which in this case is Canadian dollars, per 1 foreign, per 1. Here's one conversion then. On the other side, it's the flip of that. This is saying that it's this many foreign, so this many Canadian per dollar per $1. That's what. Let me move that over. That's the other one we could have used. They're not equal. They're two different conversions that you have to kind of pick apart to read. So I just chose this first one to plug in, but I could have used the other one also. I should have still gotten something close to 1.02. Does that make sense?
Yeah.
All right. Actually, here, some of you might be more familiar with this. If you're not, just completely ignore me, because some of you have taken a math class with me before. For example, familiar with this conversion? Some people also might be familiar with this conversion. They both will change your kilograms to pounds, for example. You wouldn't do this. That's not, it's the same thing. You wouldn't set these equal to each other. They're two different conversions that you can use.